Hi folks, this is a video on analyzing graphs of polynomials. This goes with section 6.8 in your Algebra 2 book. Today our objectives are to sketch the graph of a function from factored form. We're also going to recognize a turning point as either a local maximum or a local minimum. We'll see exactly what that means. And then we're going to identify the least degree of a polynomial by the number of turns in the graph. So if you notice here, the last two examples, the last two objectives, really talk about turning points. So that's going to be a major focus of what we look at today. So let's look at a problem here. You might want to go get some graph paper if you don't have it already. I might want to pause it first. We're going to use the x-intercepts and the end behavior, which we haven't seen in a while, but we're going to use the end behavior to help us graph this polynomial. Okay, so here's what I'm going to do. First of all, I'm going to get some x-intercepts. So if you notice, we're in factored form, so this is actually kind of nice. I'm going to take each of these factors, and I'm going to set them equal to 0, and I'm going to get my x-intercepts. Okay, so that tells me that at -2 I have an x-intercept, and at 1 I have an x-intercept. Okay, so what does the end behavior tell us about this function? I'm going to get this stuff out of the way. Well, I don't have this all multiplied out, but I do know that this is degree 1 for that factor, and here I have degree 2, right, for that factor. Excuse me, that's just being squared. So together, I'm going to have an x cubed. So however this works out, I'm going to have f of x equals, I know it's going to be an x cubed, and I know that my leading coefficient is going to be something positive. In this case, I think it's going to be positive 1/4. So I have a cubic, and it's a positive leading coefficient. So I know the end behavior is going to look like this. It's going to go up to the right, and it's going to go down to the left. So I'm going to make little marks like that on my graph. Down to the left, and it's going up to the right. Oops. Okay, so how can I make that happen? Well, another thing I need to notice about this, this factor of x minus 1, it's squared, right? So that means that there's a double root happening at 1. So it needs to be bouncing off the graph at 1. It might be bouncing like this, or it might be bouncing like that. Well, we need to figure this out. Well, let's look at the end behavior. End behavior is going to give us a big clue here. Well, I'm starting down here, right? I know it's going down to the left, and it's going up through this x-intercept, and it looks like it's going to have to come back down and then bounce off and then go back up to that end behavior like that. So I know it's supposed to look something like that. The last thing I'm going to do is I'm just going to check my y-intercept. I'm going to get all this stuff out of the way. I might need to modify that graph in just a moment here. So I'm going to find f of 0. I'm going to find my y-intercept just by plugging in 0, right? 0 minus 1 squared. And if you calculate this, we're going to get, I think we should get a half out of this. So it looks like my graph's a little bit too high here. It's not too bad. It's pretty darn close though, right? Maybe it's something more like this bouncing off. But again, I use my x-intercepts, I use my end behavior, and I also use my y-intercept to get a pretty darn looking and quick graph of this polynomial. So you folks actually have enough information right now to try numbers 4 and 5 from your textbook. Those are actually doable just after that little bit of our lecture. Okay, let's talk about turning points. Well, I'm going to start this off by just a very intuitive graphical way of looking at turning points, and then we'll look at the actual textbook definition here. So if we have a polynomial like this, our turning points are going to be this point there, right? That's where a graph starts turning. It goes from going up to going down. And then we have another turning point down here where it was going down and then it starts going up. So those are what we call our turning points. Here's our formal definition of whether a turning point is a local maximum versus a local minimum. So both of these are turning points. Here's the textbook definition. So the local maximum is the y-coordinate of a turning point. And it's a local maximum if it was higher than all the nearby points. So this first one here in red is higher than all points in its little neighborhood, right? If we go too far away, if I look way out here, way out to the right, well, that point, yes, is higher than our local maximum right there that I arrowed there in green, right? That's our local max right there. But we don't want to consider points out of that far away. We just want to kind of stay around this area here. And it looks like that's the highest spot in that little localized area. Same thing goes for a local minimum. The y-coordinate of a turning point is a local minimum if it's lower than all the nearby points. So this one over here in green, this one here in green, is a local minimum because everything in its little neighborhood is higher than it, right? It's lower than everything else in its neighborhood. Okay, so that's the idea of a local maximum and a local minimum. And again, both of those are turning points. So let's take this idea and put it in the context of functions. So what I want to do here is a little exercise, very quick one here. And I want us to make a connection between the degree of a polynomial and the number of turning points. Okay, so what if I told you that this was degree 3, and you should be able to look at this and determine the number of turning points. So first of all, how many turning points are there? Well, there's one here, there's one there, there's 2 turning points. Okay, let's look at the next example. So what if I were to say this is degree 4? How many turning points are there? Well, there's 1, 2, 3 turning points, right? So degree 4, and there's 3 turning points. So can you make a connection here between the degree and the number of turning points? Okay, well, if you said that the number of turning points has to be 1 less than the degree, right? 1 less. You've got the basic idea here. 1 less. As it turns out, that's not all the way true. That's most of the way true, but it's not all the way true. Here's one more example here. I'm going to draw this one out by hand. Y equals x cubed looks like this. That actually has no turning points, right? So it's not just that it's just 1 less, but it tells you that the number of turning points is at most 1 less than the degree. There's no way I can have a degree 4 polynomial that has 4 turning points, or 5 or 6 turning points. But at maximum, it's going to have 3 turning points. So that fits the bill over here. If you look at this, the y equals x cubed, that's degree 3. At most, we would expect to see would be 2 turning points. In this case, there's no turning points. So if you want to see the formal definition, this is from your book here. It's kind of a mouthful, so I wouldn't be too worried if you didn't. Definitely don't memorize this, but you should understand the idea behind it. The graph of every polynomial of degree n has at most n minus 1 local extrema or turning points. Sorry about this. Furthermore, if a polynomial has n distinct real zeros, then it will have exactly n minus 1 extrema or turning points. Again, that's not so much a big deal as just understanding that the maximum number of turning points is going to be 1 less than the degree. Okay, so let's see what this does for us here. Well, question, there's 2 examples here. There's there's a function in function form, right, written out algebraically, and then we have this graph over here in B. Okay, so which of these functions has the higher local maximum? And then the second part of this is, well, where does it occur? Well, let's do the easy one first. Okay, so here we have our, well, is probably a cubic, although I guess we can't actually tell, but it looks like it's a cubic here, right? We have two turning points. Here's our maximum, right? Imagine it's the top of the hill, that's our maximum on the hill. And it looks like this height here is at 1, 2, 3, 4, right? So this has a max of 4. Well, in our function here, f of x, I can't tell what the maximum is just by looking at this function. In fact, it actually takes calculus to do this, and we're not going to go there. We're actually just going to use our calculators. So this is actually kind of nice for us here. So what I want to do here, I'm going to go ahead and get my calculator going here. So here's my function. This is actually the exact function that we just had there. I'm going to go ahead and take a look at this graph. Hopefully it actually comes up here. Here it goes. And let's see, well, where's my maximum? Well, there it is. I've located it. What's the y coordinate of it? Well, 1, 2, it looks like. This has a max of 2. So I'm actually going to get rid of this and go back to my other screen here. So this had a max of 2, as opposed to my max of 4. So it looks like the graph has the higher maximum. Okay, now where does it occur? Well, the maximum is the y value, right? It occurred when x equals -1. So that's when it occurs in the actual value of the actual maximum is 4. So just a little recap here is this statement here. The maximum or the minimum is the y-coordinate. So if I'm actually asking about what the maximum is, think about it like this. If I had a time and temperature graph, right, or time and temperature function, you know, temperature in terms of time, right? If I were to ask you what the maximum temperature of today was, would you say 2 o'clock? No, you would say 43 degrees or 70 degrees, whatever the temperature is, right? We want to know what the output is at that particular time. We might want to know when it occurred, but the actual maximum is the y-coordinate itself. Okay, so let's see what we've done today. Again, here are our objectives. Did we sketch the graph of a function from factored form? Yeah, that was like one of the first things that we did. Okay, did we recognize a turning point as either a local maximum or minimum? Well, that's exactly what turning points are, right? If it's a turning point, it's either going to be a maximum or it's going to be a minimum. And did we identify the least degree of a polynomial by the number of turns in the graph? Well, yes, that's exactly what we were looking at back here, right? When we said, okay, the degree was 3, for example, in this first one. Oops. Degree was 3, and it told us that there were 2 turning points, right? Or if the degree was 4, we have 3 turning points. So here's a wrap-up question for you. If we have a function that has 7 turning points, if we have 7 turning points, then what is the minimum degree that our function could have? We might have more than this, but what would be the minimum? Okay, if you said that it would have to be at least, again, at least degree 8, then you got the idea. Okay, I hope you guys enjoyed this video. At this point here, you should be able to do the rest of the homework assignment, which includes, you might want to rewatch the video and finding local maxima and minima using your calculator, because we just kind of looked and graphed it, and we kind of eyeballed it. But you might want to actually watch that video because it goes into a little more detail. It's a quick one, just 2 minutes. But anyways, hope you enjoyed this, found this enjoyable, and I'll see you guys next time in class.